Hi everyone, my name is Matt. I'm going to sit and stand a little bit today. So I'm talking about Dask. Dask is a library for parallel computing in Python. I've given a lot of talks about Dask in the last few months, and I'm trying to give new content in every talk. So this will be like a little bit of overview and then a particular topic within Dask. This will be very different content from the tutorials if you're here on Friday. So as an overview, Dask is a library for parallel computing. It was originally designed to parallelize libraries like NumPy and Pandas, two sort of core libraries within our ecosystem. However, what we found is that the system that we built in order to parallelize these libraries was useful for other arbitrary computations as well, systems that weren't just big arrays of big data frames, and that has ended up being, surprisingly, as useful or maybe even more useful of an application. So let's, it should be slightly refreshed. These talks are online, and as you'll notice, there's now a link. So, as I said, I've given a few talks recently. So if you want a more overview talk, you can go to the SciPy talk here. That was given in 2012 and 2016. Just talking PyGothams, more about Dask data frames. And this talk will be more about fine-grained task scheduling. So technically, how do we schedule sort of more arbitrary computations? So some of this will be technical, some will be overview. Hopefully there's something for everyone. So, in the beginning, there was NumPy, and it was good, except if your data was larger than the RAM, or if you wanted to use more than one CPU. NumPy looks kind of like this. You have an n-dimensional array, and there's a bunch of functions that efficiently compute on that array and produce some other n-dimensional array. Dask array was the first project that came out of Dask, and we created one large n-dimensional array out of many small NumPy arrays. This let us use many cores. It also let us scale out to disk. It also let us work on a distributed cluster. So n-dimensional array algorithms are hard. There's a lot of interesting algorithms in there that are sort of more sophisticated than typical database kinds of algorithms. And so this sort of required a lot of coordination. So Dask became very, very good at coordinating parallel algorithms. After we had Dask array going fairly well, the obvious thing to do was to parallelize pandas. And so with the help of a lot of pandas developers, we made Dask data frame. And similarly, Dask data frame is one logical large data frame composed of many small pandas data frames. So it's pandas under the hood, and we're just calling different pandas functions every time. This can again run on your laptop using all your cores, scaling out to your disk, or on a cluster. So let's see that work on a cluster. This is usually the fun part. Oh, great, that's actually pretty good resolution. So on my right, we're seeing the status of the cluster. On the left, I have a sort of standard Jupyter notebook. And what I have here is I have 6 CSV files that have the first half of the 2015 New York City taxicab data set. So this is all the cab rides in the city of New York of 2015, think January to June, reading from HDFS. And it has broken up our 6 CSV files into 91 different blocks of bytes. So these green bits is the report of one core on my 24-core cluster, pulling off some bytes from HDFS. And after that, there's a call to pandas read CSV to turn those bytes into a pandas data frame. So what this just did is this, on these 24 different processes, on 3 nodes, it created 91 different pandas data frames that are currently sitting in memory on those 3 computers. Okay. And I have this one object, this Dask data frame, which is coordinating all of those little pandas data frames. And it looks just like a pandas data frame, and it satisfies a subset of the API. So there's some nice data here. We've got all the rides that happened, when someone was picked up, when they were dropped off, how many passengers there were, a breakdown of the fare, what the tip was, etc. And we'll have to load this data into, it's not that big, it's 28 gigs. But it'd be uncomfortable on my Mac, but it feels very comfortable here on this cluster. So if I do an operation on this data frame, let's say we'll compute the length of the data frame. How are we going to do that? So on this right side, we're seeing all the computations that all the cores have done over time. So for example, this particular core spent 700 microseconds computing the length of one of the data frames. So we compute the length of all the intermediate data frames, we communicated all of those data frames to one machine, all those links to one machine, and we then summed that up. And in total, that took something like, that's tens, hundreds of milliseconds. So we got back a nice response in nice human interactive time. Okay. So that's how Dask works. Dask coordinates many Python calls on many different computers and coordinates them together. So this is like Dask data frame. Use that on, to produce data frame computations. Computing the length of a data frame is not particularly hard. Let's do something more complex. Let's see how well New Yorkers tip. So we're going to throw out some bad rows in this line. We're then going to make a new column, which is the tip fraction. So is it a 20% tip for this ride or a 10% tip for this ride? Then we're going to group by the hour of the day. So using some nice, pandas datetime functionality. If people are familiar with pandas, this should look familiar to you. And we'll just ask the cluster to compute that for us. And it does that doing lots of different group bys and all different computations. It sort of combines those results, does other more group bys, lots of fun things. You got this nice result in about 3 seconds of computation that New Yorkers tip extraordinarily well at 4 a.m. Like really well. It's 38% here on average. So, we're getting some nice data science out of an interesting data set at scale. This is a very small cluster, a very small problem, but this scales up quite nicely.
Question?
Go for it.
So does Dask, for those of us who have no idea what Dask is, does Dask come with the UI?
Yes, the question is, does Dask come with the UI? And yes, this is, if you were to pip install Dask and distributed, you'd import Dask, you'd start something up.
And then, is it assumed that we're going to be working on a cluster? Is that sort of like the ideal use case for Dask, or is it also fine if we're using a personal machine for some reason?
Yeah, so the next question is, I'm going to repeat questions just for the video. Next question is, does it need to work on a cluster or does it work on a machine? It works just fine on a single machine. Actually, for the first year of Dask's life, it was just on a single machine because we found that most people had problems in the sort of like 10 to 100 gigabyte range. And they were very well served with their laptop or even just a big workstation. Even like this problem is way faster on a workstation than on a cluster. You can get this down way faster on a big, heavy machine. So yeah, Dask scales down very nicely. It's pure Python, easy to install. I'll talk about some of these topics as well in the future. So that's a big data frame. And for a lot of people, that is really what's very useful. However, many problems don't fit into a big array or a big data frame. There's actually a lot of problems that when we first started this, people would come to us and say, okay, we have this interesting problem. And they're like, okay, great, I've got this big data frame. How do I shove my problem into a big data frame? And that shoving process was awkward. We were trying to rewrite a lot of code, and it wasn't very natural. Fortunately, the system that we built to build Dask Array and Dask data frame, Dask, just Dask the core, we found that was still very applicable in these cases. And so in many cases, someone had Python code and we could parallelize it well using just Dask. So again, Dask is not Dask data frame. Dask data frame is a module built on top of Dask. And Dask is a general tool for parallelizing computations. So here's a script of code that I'm going to walk through. There's some parallelism here. There's a lot of for loops and list comprehensions. And we're just going to walk through it, see what it looks like, and get a sort of intuition for computations that we can parallelize that are not data frames, they're not maps and filters and group bys, they're more custom. So we're starting out. We're going to load a bunch of, we call some load function on a lot of file names. And here I'm going to represent these computations. So circles are little functions and data boxes are results. We've got 10 file names. We're going to call load in all of them. So this is obviously parallelizable. I'm going to load in some special data set, some reference data set, maybe from some SQL database. And it's a different computation, but it can still be run in parallel. It's still present here. Then I want to normalize all my pieces of data against that special piece of data, that normal reference database, that normal reference data set. So here, this is not quite a map. It's something slightly more complex, but it's still clearly a lot of parallelism here. Maybe each of these results is for one day of data, and I want to maybe take every third day and do some sort of rolling computation. So here I'm taking every third data set, and I'm doing some sort of rolling computation. And down here you can see some normal Python code that sort of affects that computation. Here I'm running with Python, and this is actually how you can use Dask as well to do these same things. So of all of those outputs, we want to consider all pairs and you compare them in some way, but that's too many things. We're going to take a random subset of 20. These are all operations that I sort of see people using commonly in the wild. Here's just sort of a toy problem, but these are sort of some things that are representative of maybe some things that you do. Then we'll find the best one, do some sort of reduction. So that computation, actually have over here. So I'm going to sort of mock out some simple Python functions for all the functions we just saw. And then using this project Dask delayed, which is described well in a previous talk, we can just sort of take that function, and whenever I call that function, don't actually call it locally here, but instead add it as some lazy value to some task graph. Okay, so we're sort of marking this function as something you should do later. Then we're going to run this same code that we just went through, and let's go ahead and visualize what it looks like. So Dask built up that graph for us of parallel computations. If we want to, we can now connect back to our cluster and ask our cluster to compute that computation for us. Okay. So we had this sort of arbitrary graph, and Dask is able to compute that arbitrary graph for us in parallel. It's sort of a small computation for this cluster, so let's increase some numbers. We've got 100 files, take 1,000 samples, just to sort of be a bit more flashy. So you're seeing here is Dask is working on our computation well, it's being fairly responsive, and it's operating on custom computations. Okay. So I think I'm going to stand up for a bit just to be a bit more engaging. Okay, so this flexibility is useful. We can write parallel code in a way that is actually fairly similar to how we write normal code. It also lets us do more complex algorithms, which is pleasant. It's also tricky to do well. A lot of this talk will be about how it is tricky to do well and how we sort of try to overcome that challenge at a technical level. So normally, when we solve these problems, we use some high-level parallelism project, something like Spark or a SQL database or some distributed array library. These always sort of ask us to rewrite our computations in some small set of operations. So in Spark, this is map, filter, group by, join, etc. In SQL, it's a SQL language, or linear algebra. If you look at something like Spark, all Spark operations roughly fall into 3 categories. There's map partitions, so anything that's embarrassingly parallel, like map or filter. There's shuffle, so an all-to-all communication, something like group by or join. Or there's aggregations, something like min or max or distinct. And Spark has optimized the heck out of these 3 operations, because everything is based on those. Okay. So if you build these 3 things, you get a sort of database-like project. Okay. But as you've seen, sort of some problems don't fit into this model. Sort of show a few. So here's our custom pipeline problem from before. So ETL problems are fairly well represented here. So there's projects that do this, systems like Luigi. So this picture of sort of an interesting graph is on Luigi's front page. Similarly, there's things like Airflow. And this picture of an interesting graph are on Airflow's front page. These are 2 libraries that are used for this sort of common data engineering task. There's other things too. So if you want to do efficient time series computations. So here I've got a data set that's partitioned by month. So all my pandas data frames, I've got a data frame for January, data frame for March. But I want to do something on a weekly basis. So we need to sort of take a sliver of data from one and sort of share it across to the others. This sort of nearest neighbor computation. That's something that's hard to do with map, shuffle, reduce. So Dask data frame can do all of these things. I'm going to show you. A rolling operation, so it's the same sort of deal. And dimensional array operations are actually quite interesting. So here I'm creating a 2-dimensional array. I'm taking the sum along some axis. And so this is actually doable with map and aggregate. But if I want to say take the transpose and add it to itself, this computation sort of is now tricky. This is not like a standard computation. If you're sort of, these graphs are fun to look at. You don't need to understand what they do, but they should get the impression that they're sort of fun and sort of strange. And so the challenge here is computing these strange graphs. Here's a matrix multiply on top of the transpose. And we can sort of keep composing these things to make them more and more complex. This is actually fairly mundane. This is fairly simple. So there's also modern algorithms. So if you want to do sort of an efficient, numerically stable SVD, here's a computation that does it. It was released in a paper a couple years ago that was written into Dask by the author. And it's non-trivial. If you want to do it with an approximate algorithm as well, it gets a little scarier. So it's sort of arbitrary graph execution is a new thing, sort of. And it does 2 major values. It eases developer burden. It's much easier to write algorithmic code. It's much easier to sort of translate your sequential code into algorithmic code, into parallel code. It also allows you to use more sophisticated algorithms, allows you to tackle more custom applications. But again, it's sort of hard to do well. So arbitrary graph scaling is hard. For example, if I had this graph and I had this cluster of computers, which computations of this graph do I send to which computers? And when do I communicate the results from one computer to another? And when do I release data? Those are all questions that are hard to answer. In fact, it's known, if you optimally doing this, if you know all of the information is NP hard, which computer scientists will know is a synonym for very, very, very hard. Yeah. And then doing this, so this is the same computation but a slightly less trivial problem. Doing this scalably, so these graphs often end up being hundreds of thousands of nodes large. Doing this scalably requires that we do it in linear time, which computer scientists know means not too slow. So fortunately, we can do pretty well with heuristics. And so Dask is the sort of core task scheduler of Dask is a collection of these heuristics that works pretty well on all the problems that we've thrown at it so far. So array problems, data frame problems, machine learning problems, etc. Dask is a dynamic task scheduler for custom arbitrary computations. It works well on single machines or on clusters. And it has around a 200 microsecond per task overhead. If you're used to MPI, this is a very long time. If you're used to most other things, this is pretty fast. We can process around 5,000 tasks per second, just in overhead. Handles locality, resilience, etc. On top of Dask, we've built things like Dask Array for NumPy compatibility, Dask data frame for pandas and such. There's some collaboration with machine learning folks, other things. It's accessible in Python. This is a little bit small. Let me see if I can. I'm borrowing a laptop today, so yeah, I'm just not going to try. You can pip install it. You can content install it. You can actually read the source code. It's actually all pretty understandable. How much time do I have left?
Like
20 minutes. Great. Okay. So we use some mechanism to create some graph. That might be Dask data frame. That might be this sort of arbitrary computation stuff we were seeing before. And now our job is to execute that graph in parallel. So this is a trace showing that computation running on 4 threads on my local machine. This is a pipeline grid search using scikit-learn computations. See, 4 little workers, traveling through this graph, picking off tasks, running them, completing them, sending that data to other workers, releasing the data when they can. This is sort of a trace. This is sort of the thing we need to figure out how to do well. And doing this well strongly impacts our performance. Doing this poorly causes everything to break. So, nothing that I'm going to talk about from here on out is anything you need to think about. This is just, I want to convey some understanding of how dynamic task scheduling works and the sort of things we think about, so that when you use Dask, you sort of know what it's doing for you that you never have to think about. So you can safely ignore the rest of this talk. So, Dask does everything in the small. It has no idea what an array is, or what a data frame is, or what a shuffle is, or reduction is. It knows what a task graph is. And it takes a little part of that task graph and it figures out what to do. And all of the decisions are sort of done at that sort of micro level. But out of that, if we make the decision just right, we get good macroscopic behaviors. Almost. So also, all decisions are done in constant time, almost. So here's a sort of a very simple problem. We have 2 computers. We want to compute this computation. So we're calling F twice on 2 inputs. Then we're calling G on their results. Now, we're calling F twice. Maybe F takes a while. You might want to call F on each of our different computers. We've got two computers. So let's do this in parallel. Now we've got to move one of those results to the other in order to run it in order to run G. So we need to look at X and look at Y and see which one's smaller. We want to move the smaller one in order to reduce our network costs. Unless, of course, maybe F is very fast and its results are very large. Then it might actually be faster to run both Fs on one machine and not use parallelism at all. Or maybe G has to run on a GPU, and only one of our machines has a GPU. So there's a lot of interesting constraints that can come up here, and we need to sort of think about how to measure things real time, how to sort of compute this thing well when we don't know a whole lot of information ahead of time. So Dask is dynamic, meaning that it learns on the fly. So here's a very simple graph. Which function do we run first? We have both Fs are available. And which one do we run first? So we're going to choose to run the left one first, because something depends on it. It's sort of on a critical path. We can't finish our computation until everything's finished. So we're in the left one. Similarly, in this case, which function should we run first? The left F or the right F? So we should run the one on the left again, because that will expose more parallelism. Once X is in RAM, we have lots of other choices. Since we have more workers, maybe we can sort of flood those workers with extra tasks. we can be more parallel. In this case, we have two functions that depend on different amounts of data. Which one do we run first? We run the one on the right, because that will allow us to free up this data once it finishes. So we can free memory and release our resources. So there's a single system, Dask, scheduler in the middle, that does all of this logic, that coordinates this logic. Someone very thoughtfully put a bottle of water up here. And there's a sort of a fleet of workers that do whatever the scheduler says. The workers hold on to the data and they communicate amongst each other to share results, but the scheduler coordinates everything. Sort of a very, very good secretary. Then there's a bunch of clients, us, connecting to the scheduler, asking the cluster to do things for us. So once we've decided a task we want to run, let's say we have 2 workers, we'll assign that task to some worker. It'll be sort of pending. Once that worker is free, we'll actually send the information about that task, about that function, over to the worker, and the worker will start processing it in a local thread on some other machine somewhere else. Once it finishes, it will hold on to that data in that worker until someone needs that data. It might be another worker that needs some result that it just produced, or it might be the client saying, actually, the last function you just computed, I want that one. And it will send it back to the client. Now, if we have some other function, f of x, so a function that depends on the result we just made, where do we run it? Do we run it on the top machine or the bottom machine? So we choose to run on the top machine for data locality. We don't want to move x around. Moving data around is sometimes expensive, especially when with large NumPy arrays or pandas data frames. They're many gigabytes large and your network is slow. So we process it, we get some result back. Similarly, if we want to compute on 2 variables, x and y, but x and y live on different machines, okay, so we got to choose one of the machines and move one piece of data over to the other one. Which do we choose? In this case, we're going to choose to put it on the bottom machine and then move data over. And the reason we do this is because y probably takes up more bytes in RAM than does x. So we need to measure the number of bytes that every piece of data in our cluster takes up, so we can make these decisions well. In a more common situation, you might have this case where we're running f of x and y. So we look at our 2 workers, we say x and y are both on the top. So maybe we want to run on the top. We also see here that there's a lot of work pending here on this top worker. It seems to be pretty saturated. So we may want instead to move the data down to a lower worker. This decision depends on a few things. Depends on the expected runtime of all of the functions in the queue on the worker. It also depends on all of the data we'd have to move. There's a calculation we have to do there. So you do a lot of measurement in order to make this work well. Similarly, we might want to, a new worker might come on, we might want to steal some work. And we need to sort of find the right tasks to steal based on the expected runtimes, based on the data we have to move. Okay. So intelligent scheduling requires measurement. And Dask does a lot of measurement. That is also what gives us these nice visuals we saw here on the right. Dask is doing a very, very thorough job of measuring everything and using that both in scheduling and in visualization back to the user so you can understand where your algorithm is slow. So we measure the number of bytes using the size of protocol. We measure runtimes. We ask the process in case the size of protocol isn't working well. We measure network distance. Every once in a while we heartbeat and we actually see what the time back was. We do lots of other things. Other optimizations I'm not talking about at all. So we can gracefully scale up and down the cluster based on load. We might compress arrays or not. Sorry. So we might have a gigabyte array we need to move, and we decide if we want to compress that or not. And we might take 5, 10 kilobyte samples of that array and try compressing them and see if it's worthwhile or not. And then we choose to compress or not compress. It's something that ended up being very important for a lot of array computations that we do for everything just because we can. There's lots of other optimizations that show up. If you want to compute many small tasks, we end up batching them. If you want to do many messages in a small time, we end up having batched them as well. We still use data to disk. All of these optimizations were necessary in order to make Dask array and Dask data frame work, but none of them were specific to arrays or data frames. So Dask has no idea, again, what an array is or data frame is. So as a result, all of these optimizations work everywhere, including on custom algorithms. So it was I was working with scikit-learn developers a little while ago, and I said, okay, I've got this computation. I need to move this particular piece of data to all the workers, because they're all going to need it, and we want to do that quickly. to make all these functions work. And I was like, just try it out and see if it works. And it just worked. And so even on some more sophisticated algorithms, things sort of just work a lot. You don't need to think about your communication as much. So doing this well in Python was tricky. So Dask is a pure Python library. And these graphs can scale out fairly large. I routinely generate graphs of sort of hundreds of thousands, a few million. And we spend around 200 microseconds per task total overhead. You track one task throughout its entire lifetime, so how much it takes up in the scheduler. It takes about a kilobyte-ish of bytes in RAM. In order to do this, we have to use just byte strings and core Python data structures in Python, which are actually quite fast. The core Python data structures in Python are fast. Like the Python dictionary is only 5 times slower than the C++ standard library dictionary. Python is actually not bad at these things. As a result, also, the code is fairly intelligible. There's not a huge class hierarchy. If you know for loops and dictionaries and sets and a couple of the data structures, you can actually understand most of the policies that are inside of Dask. You can go right now into github.com/dask/distributed, the scheduler. You can see the policies. You can reason about them fairly easily. It's accessible to this community. So people often ask, how does Dask compare with Spark? They both seem to do big data things. And they do indeed both do big data things. So I am very biased, right? I work on this thing. I'm also very ignorant. So please, ask someone smarter than me if you actually want to make this decision intelligently. So a few differences. First, Spark is firmly established and Dask is quite new. And then the other obvious difference is that Dask is written in Python and Scala is written or Spark is written in Scala. So 2 large differences. If you like Python, if you have Python developers, Dask might be something to look at. More focused technical differences. Spark has largely focused on SQL-like or SQL plus computations in that sort of map, shuffle, reduce paradigm. Dask, because we've been focusing more on sort of the PyData space where there's more interesting algorithms like n-dimensional arrays, machine learning, non-trivial machine learning, we've had to be a bit more open in general in our execution strategy. So one way to sort of make this decision easily is if your computation falls into the map, shuffle, reduce paradigm, Spark is probably a pretty good way to go. It's pretty mature. You won't get fired for choosing Spark. However, if your computation is a bit more wacky, that's my technical term, then Dask may be suitable. Similarly, Dask can do some things similar to Airflow and Luigi and Celery. It sort of operates in this sort of low latency, generic task farming mode. So Dask is generally better at computation. Interactive computations, so our overheads are lower, our latencies are lower, because we needed to really optimize for those things. We think about the right way to compress data, which is not something that most sort of ETL pipelines think about. Interworker communication is a big thing. However, Luigi and Airflow and Celery all have a huge number of features that are really useful for people doing data engineering workloads that just Dask doesn't have because it didn't grow up inside of the ecosystem. We could build those. There's nothing fundamentally stopping us from doing that. Dask, I would claim that Dask, the core library, the scheduler, is more sophisticated than what you see in most other places. But it sort of hasn't had the same evolution in this space for feature set that you find in Airflow and Luigi, which is hugely valuable. Right? The feature inside of Airflow and Luigi save developers many, many days of time. So that's it. Some final thoughts. So Dask is a library for parallel computing in Python. You can do things like parallel pandas, and I suspect for a large quantity of the room, that's what is most exciting about this talk, that we can do panda stuff on a cluster, and it seems to work pretty fast. But there's this thing beneath it, which ends up being very useful for a variety of use cases, both for as well as for algorithm developers, so academics doing interesting things, but also for institutions that have a cluster, have a bunch of Python programmers and want to marry the two, and want to have sort of an easy transition for those users. So just sort of like, got this code, I want to send a bunch of it to the cluster. I don't want to have to think about rewriting stuff. I just want to activate this cluster for me. Dask seems to be a fairly low barrier to entry tool, and it doesn't require a whole lot of code rewriting. We also dived into a bunch of complex scheduling stuff. Distributed dynamic task scheduling is far more complex than what I presented here. But hopefully these sort of problems give you an idea of the sort of things you think about when building out a distributed task scheduler. Hopefully these give you a good idea of sort of what sort of things you should ask for from your distributed computing platform, sort of how to reason about what they're doing for you. Okay, so that's it. Quick acknowledgements. So I work on this. I'm probably the loudest Dask developer, but there's countless others, both in the continuum and with other open source people. Also, there's a lot of buy-in from the sort of core PyData SciPy developer community. So the Dask data frame stuff was done with the Pandas developers. They're probably, of the past 10 pull requests, core Pandas developers are probably responsible for 8 of them. The NumPy developers worked on Dask Array. Scikit-learn developers are now pretty active, trying to figure out machine learning things. The Jupyter developers have been very helpful in figuring out all the network stuff. So a lot of core buy-in from the community, which is encouraging. There's nice funding, so I'm paid to work on this full time, which is nice. You should thank Continuum Analytics a little bit. You should also thank the X-Data program from DARPA and recently the Gordon Betty Moore Foundation, their data-driven discovery program. And that's it. If you have any questions, thank you. Please.
How well does Dask scale for using custom-built objects, and what methods need to be implemented for Dask to use those objects in a distributed fashion?
Right. So the question is, how well does Dask scale with custom objects, and what should I do in order to make sure they're Dask friendly? So the distributed scheduler calls Python functions on Python objects. End of story. So anything is fine. Some things you should do to maybe make things more nice, you can implement the sizer protocol. If your data is if you're allocating a lot of data, the sizer protocol is something you implement that sort of tells Python a rough guess of your data footprint, which Dask would appreciate for scheduling. And that's an easy thing to do. It returns an integer. You should also make sure that your things are easily serializable. Dask uses Pickle or Cloud Pickle, which can do most things. In practice, people don't care, and they just use it naively and everything works. But if you want to be very nice, I would appreciate implementing the sizer protocol. Answer your question? Great. In the corner.
Hi, I have 2 questions. One related to the previous one. So if you do have a custom code class or code, do you have an you're instituted on a cluster? Do you have to deploy your code everywhere, or is that send out your?
Yeah, so the question generally is, how do I distribute my software on a cluster? Does Dask help me there or not? So there's a few different solutions. Most people who use Dask maturely on large systems use something else like Docker or Kubernetes to manage some of that for them. And Dask sort of composes nicely with those systems. There are some hacks you can do within Dask as well. So Dask is happy to distribute egg files or Python scripts out to all the workers and make sure that they're running locally inside the path. There's a way to distribute content environments using Dask. But I would say also for just dynamic code you write in a notebook, that'll all just be serialized nicely by Cloud Pickle. So if you have a script or an egg, no problem. If you have a bunch of libraries you want to move around, I would suggest looking at something else. Continuum has things they can sell you. Docker is a great solution. Other ways of managing NFS. Generally, managing software on clusters is something that Dask doesn't really want to take on its own.
And the second, on distributed, when you're running on a cluster, and say one of the nodes goes down, will the scheduler retry whatever stuff are on there, whatever, and reconstitute any of the data that was lost before, do you end up having to run the entire computation?
Yeah, so the question is, how well does Dask handle a failed worker? The answer is pretty well. So we have a full provenance of everything that was needed to produce that particular task. It can rerun them. You can also add workers dynamically real time. So the whole system is scalable. Clients can go in and out. Workers can go in and out. It's resilient. It's elastic. Just fine. I'm going to go to this side of the room for a bit. Anyone over here?
How does Dask handle heterogeneous cluster?
Right. So how does Dask handle heterogeneity in my cluster? I might have many different racks that are some communication is cheap, some is expensive. I might have machines with different abilities. So for communication, all workers are considered equivalent. So there's no rack to rack preference or data center preference. That could be added. It's not hard to do. It's it's all Python code too. You could, if it was interesting to you, you could do it, or you could pay me to do it too. People now pay money for open source stuff in Dask. It's great. For worker heterogeneity, so there is a way to say these tasks must run on workers with these properties. So this is common. So the GPU people were the ones who really pushed this originally. I've got 100 machines, 10 of them have GPUs. I've got this big graph. These particular tasks require a machine that runs on GPUs. Make sure that these two sets are hooked up. So that is fine.
In the situation where you have a Dask data frame that you'd like to write to disk in some binary format and in parallel read it back at a later point, what would you recommend?
So the question is, what is the right binary format for Dask data frames?
Yes.
Yeah. So if you're on a single machine, I'd suggest HDF5. That's probably still like the standard solution. If you're on a distributed machine, HDF5 doesn't work well for a variety of reasons, unless it mostly doesn't work well for a variety of reasons. And you'd want to use something like Parquet, which tends to be pretty active in the Hadoop space. There's no good Python pandas Parquet solution at the moment. Something Wes McKinney's been working on a lot recently. I'm not sure how pointed or informed your question was. This is something that's in conversation right now. There's not a very good binary format for Python on a distributed cluster. There's active work. People at Capital One are interested in it. Continuum's interested in it. A lot of for-profit companies are interested in it. The open source world is interested in it.
Thank you.
Check back in 2 months. Yeah.
So when you've got a system, if you're distributing out to a system where you have a multi-core CPU, do the workers on that CPU share a memory space? Are they cross-aware of the memory allocation for that particular CPU?
Right. So question is, are cores on one machine aware of each other, and can they share data cheaply or not?
Correct.
Yeah, and so you can run, so you can certainly run Dask workers with a thread pool, in which case the workers will share memory, and the scheduler is aware of that, and will treat all of those workers as being sort of free to communicate amongst each other. So that's fine. If you use processes, that's not available. So if you're using numeric code like NumPy or Pandas or scikit-learn or Cythonized code or NumPyized code, the GIL is not a problem. Threads are great, and you should be using threads. In that case, you're totally set.
Which is default?
I think the Dask worker, if you just like type in Dask worker, you'll get threads. But there's a command line interface that's very easy to understand. Speaking of which, sorry. So there are 2 documentation pages, one for Dask, the sort of, one for Dask, the sort of parent project that has all the algorithms like Dask data frame and Dask array. The second doc page for the distributed scheduler just on its own. This is all the information I've just talked about intelligent scheduling. And the documentation here will be more than sufficient, I believe, to answer that question. Yeah. So, yeah.
So I use NumPy quite a bit for just as long as it's installed on the cluster. Anything to be concerned about with distributed tasks?
Yeah, so the question is, I use Numba. Does Numba work well with Dask in a distributed context? Yes. Yeah.
No issues, nothing.
There was an issue a long time ago that we fixed a while ago. Yeah, so it's fine. Yeah. How are we doing on time?
5 minutes.
Great. Okay.
So for this demo, you were linked up to a remote machine. Did you SSH in and run your notebook from there, or are you running Dask here and feeding it the IP or some link to start the job remotely?
Yeah, so the question is, you had a cluster, but you're also using a laptop. How did that work out? So in this particular case, I was using a Jupyter notebook that was hosted on the cluster. But you can use, so the scheduler, so the scheduler and the workers need to be close in the network, but the clients can be external. So as long as the software environment between the clients and the workers match, everything's fine. Because I have 5 minutes, I actually want to switch to actually a small extra bit of information slides if you guys are patient enough. So let's do, ooh, this is going to be fun. Yes. Okay. So, so here's a distributed scheduler. There's one scheduler, there's a client, there's a couple of workers. The client authors a graph and sends that graph up to the scheduler. The scheduler looks at that graph and finds that there's 3 nodes that can run, and it balances them across its 2 workers. A worker finishes a couple of those computations, and it reports back to the scheduler. So blue is finished here. Reports back to the scheduler, hey, these have finished. The scheduler then looks at this extra task that has to run, figures out who should run it, says, oh, both of these pieces of data are on this worker. We'll send that task up to this worker as well, thinking about data locality as we discussed earlier. The client learns about this. The client learns that these computations have finished. And it can send up other computations real time. So this isn't synchronous. This is totally asynchronous. There's a full conversation happening on all things all the time. And the scheduler can learn about that and schedule things appropriately. As a task is no longer necessary, the worker can garbage collect, the scheduler is aware of it, and things can be cleaned up to keep RAM friendly. Dask handles concurrent workloads. You can have multiple clients operating on the same workers, even with the same data. Dask is quite good at providing uniquely identifiable names and deterministic names on all computations. So if 2 people are working on the same data set and doing the same computations, they'll actually be deduplicated. Dask can load balance, and over time, there's this conversation between workers and the scheduler and the clients, and these computations occur. A client can go away, and the scheduler can remove that computation. Workers can go away, and it looks like this computation up here at the top corresponded to this computation here in the scheduler. And so we've lost that computation, but it's okay because we know how to recompute it. So this goes to your question earlier about resiliency. So the distributed scheduler is one system that coordinates all these workers, knows that locality. It's fully asynchronous. So I'm not sure if you noticed, but when I was playing with the notebooks, we submitted computations, saw the progress bars going, but then we kept working in the notebook doing other things. So it doesn't block us. It's multi-user. It's HDFS aware, so it handles fine with the sort of the Hadoop world. It also handles pretty well with the non-Hadoop world, so we have sort of people who use it from both sides. It supports things like Dask Array and Dask Data Frame, which are actually really good for early benchmarking, make sure that we had support for all these algorithms. And it's around 3,000 lines of Tornado code, most of which is isolated to a certain area. 3,000 lines of total code. So it is a Tornado TCP application. The Tornado stuff has been intentionally isolated from the rest of the policy code so that non-web developers can reason about the code. To give an example of that, let's go look at how we decide workers to use. This is a bit of the logic that we were discussing.
Can you come up with the screen?
I will. So here's a function that takes in a bunch of information about our tasks and our dependencies and what everyone's working on. They're just dictionaries of strings, because that's fast. And it determines within tens to 100 microseconds which worker to use based on all that information. And this is code that you shouldn't get immediately, but it should not be immediately scary to you. It should be something that you should feel comfortable looking at, reasoning about, and maybe hacking with. So, anyway, that's it. I'm going to finish. Thank you all for your time. I think lunch is coming up.